Hey guys, welcome to Safi Mixed. In this video, I consider a simple system of two connected masses, that is, I consider a composite system consists of two masses connected to each other through an inextensible string. And I want to find the condition for finding forces on different masses. I want to solve this problem and want to link the forces with masses, how the ratio of the masses or how the magnitude of masses affect the forces acting on two bodies. So what do we have? We have mass m1, mass m2. That means we know the masses of this body, the mass of this body, and the mass of this body. And similarly, they are connected through an inextensible rope. And the whole of this compound system or this composite system is acted upon by a force F. And when I say force F, that means we know the magnitude of F. So we want to find the acceleration of this composite system, and then we want to find a relation that tells how much force acts on this body or on this body individually. So for that, first I need to represent the forces. According to Newton's third law, a force acts on this body in that direction due to mass m2, and similarly a force acts on this body due to mass m1 in this direction. And I represent that by putting a force, that is a force F12 is acting on mass m1 due to mass m2, and it is in that direction. And similarly, a force F21 is acting on mass m2 due to mass m1 in this one direction. And there are vertical forces as well. The mass, the weight of mass m1 is in downward direction, and there is a reaction force from the surface, which I represent to be in the upward direction, in that I represent with n1. The same is true over here, m2g, and the normal force m2. There could be friction on this body, friction on this body, but I'm not considering friction, so I consider a frictionless surface over which the motion is carried. Now, since there is no motion in the upward direction, therefore, using Newton's second law, I can find a condition on m1j in 1 and m2j in 2. That is, according to Newton's second law, the forces on body m1 along verticals are n1 minus m1g. That is, I consider the upward direction to be positive, therefore I put that. If I want to write this in vector notation, I'll put a vector over it, and therefore a vector over g. And according to Newton's second law, it would be equal to m1 and an acceleration, let me call that acceleration a1 prime. But since there is no motion along the vertical, therefore this acceleration is 0, and I write this side of the equation to be equal to 0. This allows me to write n1 equals m1g. That is, the magnitude of these two forces are equal, but they are opposite in direction. One is upward, the other is downward. We have won this condition. And similarly, for the second body, I can write Newton's second law in the form. I would like to write this over here. N2 equals m2g. These forces in each pair balance each other, so they don't contribute to the motion of the body. Now, if I look into these forces, they are horizontal, and I take the left side, the direction of F positive, then this force is positive, this force is positive, and this one is negative. And I begin from the net force on M1. The net force on mass M1, according to Newton's second law, is F minus F12 equals m1 a1, where a1 is the acceleration produced in this mass. And similarly, let me call this equation 1. Similarly, the net force acting on mass m2 is the only force F21, so I write that force is to be F21 equals m1 a2. a1 is toward the left, a2 is toward the right, so they are positive to this direction. And now, if I use Newton's third law, according to Newton's third law, F12 equals minus F21. That is, third law tells us that that F12 is equal to F21 but opposite in direction, means that the magnitude of F12 is exactly equal F21. So they are equal in magnitude. In other words, I write the magnitudes to be F12 equals F21. Drop the parallel, the modulus sign. So this would be the magnitude, and I'll call this equation 3. Now, from equation 1, I can find a relation for acceleration or for relation for the force to write. Let me call this equation 2. I missed this. This is 2. So what I do now, first I add these two equations. Adding equation 1 and equation 2, I can write F minus F12 plus F21 equals M1 A1 plus M2 A2. Right? Using equation 3, I can cancel these two with each other. And using the condition of inextensibility, if the string connecting the two masses is inextensible, then we have A1 equals A2 equals A. Since A1 is toward the left, A2 is toward the right, both carry the same direction and their magnitude is equal to A. So I can write this equation in the form F equals M1 plus M2 into A. This allows me to find the acceleration of the compound system. A equals F divided by M1 plus M2. So this equation gives the acceleration of the system. We know about F, we know about masses, therefore we can find the acceleration of the system. Now, I want to find F21 in terms of F and the two masses, and that I can do by dividing equation 1 with equation 2. So I do F minus F12 divided by F21 equals M1, and for A1 I write A divided by M2, and for A2 again I write A. So this A cancels with this A, and I can write the left side in this form, F21 minus F12 divided by F21, and using equation 3, F12, the magnitude of F12 is exactly equal to F21, therefore this thing is 1, and on this side I write M1 divided by M2. So setting this to 1, I can write the equation F divided by F21, and I'm taking this to their side, equals 1 plus M1 divided by M2. And I can write this as F equals 1 plus M1 divided by M2 into F21. Okay, now I want to write this equation in another way, and I do that by writing it over here. I don't need these things, so I would like to write the equation into this form. F21 equals 1 divided by 1 plus M1 divided by M2 into F. Okay, Okay, let me call this equation 4. Right. Okay, this equation is very rich. It tells us, it gave us two very important concepts. Remember, the force acting on mass M2 does not only depend on F, the applied force. Rather, it also depends on the ratio of the two masses and how the ratio of these two masses affect F21. We want to see that, and that is quite easy. Now, if M2 is 0, that is, if we have this condition, M2 equals 0, there is no mass. When M1 divided by M2, this goes to infinity, because M1 divided by 0 is infinity. This is infinity. 1 plus infinity is again infinity, and 1 divided by infinity is 0. So under this condition, we see that F21 equals 0. That is, if there is no mass, there will be no tension, there will be no force in this rope, in this inextensible rope, and that's quite obvious. We observe that in our everyday life. So in the case of M2 equals 0, we don't have F21 or F12 according to this one equation. If F21 is 0, that means F1 is 0. So there is no force in this area. On the other hand, if M1 is 0, mean there is no mass. That means the force is directly connected to M2. And then if from this equation M1 is 0, this thing is 0, we have 1 by 1, or we have, if this say that F21 is exactly equal to F. So if M2 is 0, there is no force. F21 and F12 are 0. If M1 is 0, the whole force is acting on M2, and that's what we observe in our everyday life. And now, if neither M1 is 0, neither M2 is 0, the force is described, the magnitude of this force, F21, is determined by the ratio of these two masses. So it is the ratio of these two masses that describe how much force of this is applied on M2. And let us see, if M2 goes to infinity, what do we have then? M2 goes to infinity means M2 is very, very large than M1. Then we have M1 divided by M2 is approximately equal to 0, and under that case we would have F21 is approximately equal to F. That is, if M1 is very, very small than M2, then almost all the force is exerted on M2. On the other hand, if M1 is very, very large than M2, right, then we have M1 over M2 is approximately equal to M1. And we would replace this thing with M1. So F21 then depends on the value of M1. So it is in fact the ratio of the masses that determines how much force would act on this body. If the two masses are same, then half of the force would act on this body and half of the force would act on this body, because we can easily see then if M1 is equal to M2, then this thing is equal to 1, 1 plus 1 is equal to half. So F21 would be equal to F divided by 2, or half of F. So half of the force would act over here, half of the force would act here. So under the similar mass, we just have the half of the force acting on this body, half of the force acting on that body. And for the rest of the cases, as I explained, the ratio of the magnitude of force depends on the ratio of the two masses. Thanks for watching.